On exercise 13 and pretty much the rest of the lesson, we're going to finish off a free response question that we started back in 6-1 area between curves. So on that particular question, the setup was identical, and what we had to do is we had to find the area between these two curves, basically the sum of region R and region S. And in order to do that, we had to find the point of intersection in between these two things using the calculator, because just take a look at the two functions that were given. F of x is equal to 1 plus x plus e to the x squared minus 2x, some sort of kind of combination of polynomial and exponential function here, and then straight up quartic polynomial function for the g of x function. Okay, now we were able to avoid finding the point of intersection A here if you were to take the absolute value of the distance between those two things. However, as you're going to see, we're going to need that point A, this point of intersection, for the rest of the question. So let's see what this part of it is. This would be like part B, let's say, of that question. Region S is the base of a solid whose cross sections perpendicular to the x-axis are squares, and we want to find the volume of the solid. So let's sketch some stuff to go along this picture, namely a representative rectangle. I'm going to do that like so here. Right, and since it's perpendicular to the x-axis, it's going to be a vertical one with a delta x as the width, okay? And then imagine that this thing is going to be, we're going to have squares coming out at us on another axis. Let me sketch what those things would look like. We got a square here, and then I'll draw another one offset from that. Dip, 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 dip. So basically, this bottom rectangle here corresponds to my representative rectangle that I just drew right here, okay? All right, and so I know that that is a delta x. I need to find the volume of this thing, integrating the area of the cross section, and that area formula, since it's a square, is just side length squared. So obviously, I need to find the side length here. So the side length, this distance corresponds to the vertical distance on my representative rectangle, which is just the top function minus the bottom function. The top function in region S, this is the one that is the roughly exponential function. That's the f of x function. And the bottom function for region S is the one that's the polynomial. So it's the g of x function. So that's f minus g. Okay, so if I throw this thing in to my calculator, this is what I'm going to type. So assuming, again, that this right here, this point of intersection was A, which we will have to find. Right. So our volume would be equal to the definite integral from that A value, whatever it is, up to, let's see, this one is given to us here at 2 of f of x minus g of x. There's our side length. We'll need to square that thing because, again, here's our area formula, and then multiply it times its height. Now, definitely what did I do? I raised that to the s power. There we go. As long as s is equal to 2, it's right. Anyway, so make sure that you have this committed to your piece of paper, because you can probably guarantee that on a calculator active question that having this thing set up is worth a point or something. All right, so hopefully you took a moment to plug all of these functions, and by all of them I mean both of those, into your graphing calculator. Let's do it. All right, I think I did it. Yes, I did. All right, let me switch over here to camera. Maybe. Okay, there we go. Lovely. So our two equations are plugged in there. Let's hit a graph. Maybe I do a zoom 4. Let's see if that's big enough in order to see the whole thing, or the parts of it that I need to find, because we need to find the point of intersection between those two graphs. All right, lovely. All right, so I was able to see it. I need this point of intersection there. It almost looks like it's 1, but I recall from when we did this the first time, it definitely wasn't. So I need to go second, trace for the calculate menu. We want to choose number 5 for intersect. And we need to choose our first and our second curve. That's the blue one. It's the red one. We do need to guess. So I'll just move my cursor pretty close to it. Hit enter, or I could have just typed in 1. And now remember that this is temporarily stored in the calculator as X, but I want to restore it as A. Probably have that, not probably, definitely have that number written on your paper here. And then if you just say A is equal to this number, then you're covered with just using A in all of your little calculations when you write it on your paper, okay? So let's quit back to the home screen and hit X. I want to store that thing as alpha A, like so. And then there's that number. So let's type in the definite integral that we talked about, that we discussed earlier, math number 9. And we're going from an A up here to 2. And it was our f of x function minus our g of x function. It was exponential, which is y1, I do believe, for us. So let's do the y1 function. I need parentheses so I can square it. So y, that's alpha f4, y1 minus y2. And then we need to close the parentheses and then square that guy and then come out here and throw an x in that box. Doom, doom. Okay, and then I would report this thing to 3 decimal places, 1.283. And that should cover it. Let's look at what the next part of that question is all about. Okay, on exercise 14, same exact setup, but this time let h be the vertical distance between the graph of f and g, so right here in region S. Find the rate at which h changes with respect to x when x is equal to 1.8. This is very strange. A common practice that they do, like they've kind of exhausted all the things that they could ask about a setup like this. You got volume, you've got your area. It could be a volume with cross sections. It could be a volume of solid revolution. And then it's like, okay, well, we need one more thing. Here, let's throw something in that's a related rate kind of thing. This one's not exactly related rate because it's h changes with respect to x instead of with respect to time. So it actually is a little bit easier than that. So on my picture here, I'm going to just draw in a segment that's going to represent the length of h. And it said that it's the distance between these two functions here. So I'm going to call that thing h. So we have basically defined a new function, h of x, as being the vertical distance between those two things. And since the f of x function is always on top, I don't have to worry about absolute value. This one in region S is always on top, so we're going to go f of x minus g of x. If it's switched, of course, I'd have to use the absolute value on that thing. Okay, and we want to find the rate at which h changes with respect to x. That means I'm going to take the derivative of h with respect to x. And then, usually we write that as h prime of x, right? Or you can use a dh dx in Leibniz notation. And that should be just using the difference rule here. I just take the derivatives of each of these functions piece by piece. Right, and then I want to evaluate this at 1.8, so that just means it's h prime of 1.8 is equal to f prime of 1.8 minus g prime of 1.8. And it's a calculator thing, right? Instead of hitting math number 9, we're going to hit math number 8. And let's see, calculator and camera view. Okay, back on the home screen already. And I want to go to math and this time choose number 8 so we can get the derivative thing. So we'll throw an x in the bottom here. The function for our top function, that was the y1 for f, alpha f4 at y1. And then over here is at 1.8. Just arrow out of it and then hit minus and do the same thing for the bottom function. So we'll take the derivative, math 8, a d dx, and this time it's a y2 inside the hole, alpha f4 again, choose number 2, and then throw in our 1.8 once again. Hit enter, And we can see that the rate at which the distance is changing at 1.8 is negative 3.811 or 12 if I wanted to round that appropriately. Remember, you can just chop it off or round it, however you're feeling. Okay, and then one last part of this, and this goes back to the beginning of this lesson. As a matter of fact, for the last part, find the volume of the solid formed by rotating region R about the x-axis. So here we have a solid of revolution. And remember that this process also involves a representative rectangle, like so. Okay, and then we're going to revolve this thing around the x-axis. Okay, so we have a width here of delta x, obviously, and when we revolve this thing around the x-axis, this one's going to make some washers. It's going to have a big old white space that's inside here. So let me draw an image of what one of these washers is going to look like. Try again. All right, hey, that one is pretty sweet, right? And then just kind of turn this into something that looks sort of like a tire. All right, and then make it look real pretty by throwing in an axis here. Oh, look at that. Very convincing. All right, and if you wanted to, what we can do here is I'm going to draw in this kind of dashed rectangle, because that dashed rectangle is essentially my representative rectangle here that's revolving around the x-axis, okay? All right, so the technique here is that we're subtracting cylinders, and the big radius, first of all, is I'm going to take like this segment here. I'm going to see what it looks like on the picture, and that's going to help me calculate what that is. So that distance here is the distance from the top function, and over here in region R, the top function is actually the g of x function, so that's g of x, or I'll just write g, right? And then the inner radius that we're going to have to subtract out of this thing, that radius is right here. And so you can see that that one is the distance from the x-axis to the bottom function. Bottom function in this case is the exponential one, which is the f of x function. Okay, so then, whenever I go to set up this volume, don't forget this time, since this involves cylinders, we need to throw the pi in here. So usually that's worth a point, having that scalar right up front. And our limits of integration this time are going to be from 0 to that a that we calculated before, right? Because we're going to go up to this particular point, a. And inside here, it is this radius, the big radius squared, minus the small radius squared. So our g of x function squared minus our f of x function squared, or inner one. And then with respect to x. Now, when I plug this into the calculator, remember that, at least for me, I type this one in as y2, so I have to make sure that I put the second one in there first. Why does that make a big deal? Because we're going to get a negative answer when we should have got a positive answer if I type it in incorrectly. Okay, anyway, so back to the camera one last time to finish this thing off. Okay, throw in our pi to start off. Pi. And then we'll have our definite integral. So back to math number 8. Dang it, math number 9. Math number 9. And then this time from 0 to a. 0, scroll up here to a. A should still be stored into the calculator for me. And then I'm pretty sure all I have to do is alpha f4 and then put number 2 here. And then I can just hit the square button and it squares that for me. Minus, and then do the same thing for the y1, and then square that guy, and then throw in our delta x. There we go. And then hit enter on it. And then report 16.255 or 256 as your final answer, which Speaking of final things, that brings us to the end of this lesson. Okay, so that doesn't want to show it to me. Why did my iPad just completely restart? Okay, well, there you go. So we were able to calculate volume in a couple of different ways as solids of revolutions using both disks and washers. And, if it has some sort of known cross section, some similar cross sections, commonly squares, semicircles, triangles, and things of that nature. Remember that on this particular assignment here that we do have a homework supplement, and that homework supplement is going to be a released free response question that puts all of these pieces together for you.